Welcome to 61D, the course where we teach you modern full-stack web development. My name is Aiden, and today we're going to be covering TypeScript. We're going to start off with a little bit of an introduction to the TypeScript language before covering basic typing, typing of functions, the concept of type inference, which is where TypeScript infers what types your data should be without you having to explicitly define it. Then we're going to cover generic types, and finally casting. Timestamps for all of these will be in the description along with all other links you need. So, what is TypeScript? Sounds very similar to JavaScript, is very similar to JavaScript. TypeScript is JavaScript plus types. Types are just an annotation that says, hey, this piece of data should have this format. For instance, we could say, hey, this piece of data, we want it to be a number. And then if you try to later reassign that number to a string, you'll get an error. These types, however, are not types that actually exist at runtime. JavaScript, like we said before, is not statically typed, it is dynamically typed. TypeScript does not magically change that. Instead, this type checking occurs at compile time. As you are writing code, you can see, normally you have a linter or some tool will constantly be analyzing it. And if you do something that is going to cause a type error, you will get a red squiggly line underneath your bad line of code. This is a very important thing to realize. TypeScript does not work unless you follow its own rules. You are perfectly capable of making TypeScript code which does not follow the rules and will still have errors. But that being said, TypeScript does make JavaScript code much more maintainable because it lets you avoid a whole category of errors being type errors. And moreover, the fact that these types are just something that exists while you're statically analyzing your code and not while the code is running does mean that you get an extraordinary amount of customizability and extendability. The TypeScript type system is one of the most flexible out of all type systems in all programming languages, even though in some ways it's kind of a fake type system because they don't actually exist at runtime. So, why TypeScript? It makes your code avoid type errors. Realistically, you can't write a giant code base with many people working on it without TypeScript. Or you can use something that's kind of the same as TypeScript, something like JSDoc, which adds type annotations to JavaScript, and so therefore basically is just TypeScript. It's the industry standard for writing maintainable, readable, and robust code. So I hope you enjoyed writing JavaScript last lecture, because for the rest of the course, no JavaScript, only TypeScript. Let's write some code. To start, clone the starter code repository in the video description if you want to follow along. And again, make sure you've done setup for the course. There should be another link to that setup assignment in the description to make sure that you have everything ready to run. Just again, make sure that you have bun installed. If you get something like that, you're good to go. So start off with your blank basic.ts file, and let's look at primitive types. There's three main basic primitive types. You have numbers. So we could say let age equal 0, since we want age to be a number. You can annotate it with colon number. This green is the type. This means it's a number. We could say name equals a string. My name could be Aiden. That's your second primitive type. Third primitive type are booleans. So let's say let can vote as a boolean equals true. Right? Now that I have these type annotations, we can see what TypeScript actually does. If I try to reassign age to anything that is not a number, I set age equal to 90, we get an error. Type string is not assignable to type number, right? This is a type error. There's many different sort of slightly more complicated variations of this, but these errors are the backbone of what makes TypeScript TypeScript. As you notice, I didn't run my code for this error to generate because all it's doing is it is statically analyzing it. If I want, I could console.log age cd blank bun basic.ts, and it runs totally fine, right? There is no runtime error. It's only these compile time errors. The TypeScript compiler is running really quick as I am writing my code, telling me I have an error. Other basic primitive types are same things we covered before. You have undefined and null. So we could say let wife equal undefined because I am not married, and we could say let sunshine be of type null because I haven't seen the sun today. But what if eventually I do see some sunshine and I want to be able to say, hey, I can either have no sunshine for the day, null, or a number for the amount of sunshine that I've seen, however you'd quantify that. For that, we have type unions, which are a union of two possible types. We can instead say that sunshine is going to be null or a number. We do so with this single little vertical bar, the same bar you would use for an actual OR operator. And we can see that it's a number or null. So if we wanted to, we could say sunshine equals 10, and we would not get a type error. You can also make a union between as many types as you want. So we could say number or null or string, and then we could say sunshine equals lots. You do want to be careful though when you have a type that could be null or a number or string. You normally want to have a specific use case and reason why it could be any number of these types. That's less common with these primitive types, more common with more complicated types that we'll see later down the line, but good to keep in mind. Where you start really needing TypeScript is when you start typing objects, functions, and things like arrays. If we want to have a person, like we talked about previously, we could say const person has, we'll say a name would be Aiden, an age could be 21, and maybe we'll say sex is male. If I look somewhere else in my project, let's say I'm trying to import my person from this file, or I'm trying to pass a person into a function, I really don't know anything other than this is an object. If I want this to be a consistent data type that I can expect in many places and I know what properties it's going to have, I've got to add types to it. So how would we do this? We can create an object type. To do this, use the keyword type, and then we can say person equals name has to be a string, age has to be a number, and sex has to be a string. You typically use uppercase for types, and these primitive types are lowercase. It's just sort of the typical convention. And then what I could do is I could annotate this is a person. And then if I accidentally was trying to declare a person somewhere and I thought that age should be a string, I will get a type error. More importantly though, it also shows you what properties you need when you're trying to declare a new person. Let's say I want to have person2, which I'm saying is a person. It's going to show me the error, say specifically, hey, name is missing, age is missing, and sex is missing. So I can go add that. I can say name equals Katie, age is 21, and sex is female, like so. If you remember from our JavaScript lecture, another thing we encountered is that objects very frequently have properties that are optional. They will sometimes be defined, sometimes be undefined. So we could also add, an optional property, something like pets, which could be a string. And oh no, this is giving us errors because we need the pets, but not everybody has a pet. The way you make a property optional on an object is just by adding a question mark. Now, we may have a pets property. I have a pet bird, so I'm going to say bird, but it's not required. Then when you're accessing it, right, if I say person2.pets, so I'll say pet equals person2.pets. This is possibly a string, but it could also be undefined since the property is not guaranteed to exist on the object. Whereas if I accessed a required property, such as name, this is guaranteed to be a string. This question mark is really just shorthand for saying it is a string or it is undefined. One of the nicest reasons and features to use TypeScript is not only how it makes your code easier to maintain, but just the overall developer experience you get from it. Once I know that my person is of type person, I don't have to track down the type definition to see what properties are available to me on the object. This type definition could be in some file somewhere else. It could be imported from some external library. All I need to do is when I click period, all of the possible options are opened up. If for whatever reason this menu doesn't toggle automatically, then all you need to do is control space to open it up. Once you have a type declaration, you can also extend the declaration, similar to the idea of inheritance from object-oriented programming. Right now, we have a person which has certain properties. However, we might also want to define a type student. Now, a student is still a person, so we want all of those properties, but we just want to add a few properties to it. The way you do that is you say type student equals person ampersand, similar to like an and symbol, and then the properties that you want to include. So we could say type student equals person, and they could have a grade, which could be a number, and maybe they could have a major if they're a college student, which could be a string. You can then further extend student. You could say beyond just a student, you could have a pre-med student, and they might have more specific information about their major or about what they're doing. Type extension happens all the time. Unfortunately, TypeScript is a little bit confusing because there are kind of two different ways that you can declare a type. First off is a type, which we showed, and the other way is called an interface. to declare an interface, you simply say interface my interface. You don't use an equal sign, and then you just use the curly brackets. You could say property1 is a string, and property2 would also be a string. You can then say that some object is going to be of this type, the same way you would with a type. So we could say value, which is my interface, has prop1, hello, and prop2. There are a lot of really subtle differences between types and interfaces, which most of the time don't really matter. Generally, types are a little easier to work with and have nicer syntax, at least in my opinion. And so for the whole course, we are exclusively going to be using types. If you're more interested in some of the differences, I'll link something in the description. But from now on, we're just going to be using types. However, if you see an interface, you need to be able to recognize what it is. And the single most important rule is, in some project, whether you're using interfaces or types, be consistent. Otherwise, it's going to be extremely confusing. But I would recommend just use types. Sticking with the theme of things that exist in TypeScript and you need to be able to recognize, but I don't personally recommend you use, are enums. The idea behind an enum, it's a term that exists both in TypeScript, also we'll cover this when talking about databases, is it's simply something where you declare something has to be one of a few options. So for example, you could imagine a role in a company. You might represent it as a string, but it's only going to be a subset of options. You could say, hey, there's maybe CEO, manager, and employee as my three roles. The way we could declare one of these is we say enum role, or we could maybe just say title, is, what did we have? We had CEO, which we're representing as a string CEO. We have manager, which we're representing as the string manager. And we had employee, which we're representing as the string employee. Actually, you do not use that equal sign. There we go. So then if we declare that some string is actually going to be, if we want to use some function where we are only going to process these three possible options instead of, for example, processing any type of string, you can access one, for example, by saying const my employee equals title dot manager or title dot employee, just like that. This is going to get represented as this string, but this ensures that we know it is of this type. So for instance, we could change this, and now this would be represented by this string, but it still is the employee type enum. The better and just overall simpler way to go about it is using a union of string literals. So what do I mean by that? Here we declared something as a string, which can be any string. You can also declare a type that is a specific string. So if we were to recreate this enum, we could say type role equals not string, but instead a few literal strings. So we have CEO or manager or employee, right? Then if we were trying to declare some role, my role as a role, it won't let us type in any old string, right? Because this string is not assignable to type role. And moreover, we can use our handy dandy control period and see all of the possible string literals that we can use. Again, you need to be able to recognize enums, but doing type unions with literals like this is generally preferred. It's easier to work with and reduces the actual size of your project when it is compiled and released. And most importantly, you don't have to import enums all over the place. You can just write something that is the actual value of the enum instead of saying title.employee. Final super quick thing for our introductory section is adding types to arrays. Almost all of the time, we want all of the items within an array to be of the same type. And to do that, you can, for example, say const my strings equals string and your two little brackets to signify it is an array, and then set that to an array. Then if we were to try and add a number to this array, we will get an error. And anytime we access a value from this array, it will be typed as a string. Next up, we have functions. Almost all the time when you're writing a function, you want to declare what types are the arguments you're expecting. So we could write a function to check if a password is too long or maybe too short. So we'll say const too short, and we're going to take two arguments. We're going to take a password, which is a string, and a min length, which will be a number. Then what we could just do is we could say return password dot length is greater than min length. Well, I guess if it's too short, it would be less than min length, like so. Very simple to declare the types for your inputs. And almost all the time in TypeScript, you actually do not want to declare the return type of your function. The reason for this is that the return type is actually inferred from usage. So, for instance, I could say const my result equals too short for the password 12345 and a min length of 6, which should be a number, not a string. That's why we have TypeScript. So what is this going to be, my result, right? We can sort of see that, right, this is going to be a Boolean. It's either going to be true or false. And TypeScript can also tell that. I don't need to say what the return type of this function is going to be because the TypeScript compiler will infer it for me. If we hover over it, we can see, hey, too short takes in these inputs and it returns a Boolean. Then if we hover over my result, it says it is a Boolean. The reason that you don't want to declare your return types explicitly is that it makes it a lot easier to make mistakes. Sure, this is a TypeScript error, but this type error only occurs in one place. We could use this function 1,000 times and then every single output would be typed incorrectly because your explicit type is going to override the actual inferred type. The only reason that you might want to add an explicit return type is perhaps while you're writing the function, if you have in mind what type you want your function to return, it can make sure that while you're writing it, it is the correct type. But at the end, if it is returning the type you want, right? So we might say, hey, we want to return a Boolean. And then if there's no type errors, because the explicit type matches the inferred type, it's really best to delete it, like so. We'll talk a little more about type inference later, but it's one of the most powerful features of TypeScript. something that is a tiny bit trickier is adding the correct types to a higher order function. So first off, what is a higher order function? A function is just any function that takes another function as an argument. We've already encountered some of these. If you remember the map function and or the filter function that we talked about last lecture, what we can look at is we say nums.map. And if we remember how this works, we pass in a function that says what we want to do to each value. So for example, what we could do is just double all the values, right? So const doubled equals nums.map, right? Map is a higher order function, takes in as an argument this arrow function, which just doubles all the values that you pass to it. It's a little trickier because when we're typing the function that we expect, we have to type, okay, what are the arguments that the function expects, and what are we expecting the function to return? So let's try this out. Imagine we wanted to write a function that applied some function similar to the map function, but only applied it to the odd indexes. We could do this by saying const map odds is a function. We'll leave the arguments blank for now. And we want to do something, right? What we need to do is we need to take our array and the function which is going to do something. In this case, we can just, for now, say the array could be a string array. And the way that you type this function is you say function, parentheses. As you'll notice, this turns it yellow, showing that it is a function. Inside the parentheses, you say what parameters the function should expect. So in this case, we want the map function to, or the function we pass into map, just needs to take in a single input, which would be a string in this case, and return a single output, which would be a string. So input string. And then the return type of the function, we use this arrow operator and say it's going to return a string. So if we hover over, we see takes in a string array, takes in a function, and then we haven't said what we're returning yet. So let's actually write this function. We can do it all in line using some of the JavaScript tricks we learned before. We can return array.map, the given value, and depending on whether or not it's odd, we need the value and actually the index. We say if the index modulo 2 equals 1, we will apply the function to the input or just return the input. So it's not input, we wrote it as val. That was what that error is. So a little bit of review from last time. This is a ternary statement. It's a condition, and then we're going to do something on true. Otherwise, we're going to do something else, right? So this function is some arbitrary function, and we're then going to go pass that into the map function, and this is only going to map our odd values. So let's try this out. What we can do is we can console.log map odds, taking in the, actually numbers isn't going to work because we need a string array. So we'll say names equals Aiden, Katie, Angela. Set this as a string array. And then we need some function that can apply to strings. So maybe we'll say const first char takes in an input string and returns input dot char at 0. Right? So this takes an input string, returns a string, so we should be able to pass it into our map odds function. So we say map odds, names, and then first char. Right? If we were to change something about this function, so instead of saying char at 0, we maybe said return input dot length, which is going to be a number. Now this will throw a type error because even though it's getting the correct input, it is not returning the type that we expect. You could also do this as an inline function, right? So we could almost do it similar to the way we're familiar with our map function. Say, hey, I'm going to take some input, and this input is automatically going to be assigned as a string because we know that we're going to get strings, and then return input dot char at 0, like so. So we can cd into blank and go bun functions.ts, and we only get C for index 1 because that's our odd index. Could add another one, Elaine, can't spell, and it would apply our map function, our first character function, to only the odd indices. One other type you need to be aware of, which specifically applies to functions, is the void type. All it means is it's a function that doesn't return a value. So you could have a greet function which takes in a name, and it could not return anything, but instead, what am I doing? Arrow operator. Instead, just console.log hello name, right? And then as we see, this is of type void. So if we were to accidentally, imagine, oh, I think this returns hello name instead of actually just logging it and not return anything, const greeting equals greet Aiden. This will tell us that it's a void, so if we tried to later use it as if it was a string, we would get some type errors. Now it's time to circle back to something I talked about very briefly earlier, and that is type inference. Type inference is any time that the TypeScript compiler infers and figures out what type your data looks like without you having to explicitly tell it what type it should look like. The simplest form of this is if you declare a variable. So we could say let my name equal Aiden. We don't have to declare that my name is a string because it can just infer it from when you typed it as a string. Later, if I said my name equals 0, this will throw a type error because initially we set it to a string and now we're reassigning it to a number. This also applies to object types. You can have a value be of a certain type without ever explicitly saying that it is of that type, right? Here we have a function getName which expects a person, and it's going to give you the name of that person. I can say const John equals an object that has a name property as John, an age property of 22, and we'll give it that optional grade of, I don't know what grade you'd be in, 22-year-old, 16th grade or something like that. Then we can pass this in, say console.log get name with John, and we don't get a type error. Even though it expects a person and we never said that John is a person, the fact that John has all the required properties of a person means that this function will behave correctly, and it means that John is a person even if we don't declare explicitly that he is a person. But for instance, if we were to change this to be a number, we would get an error because that name is a number and it's expecting the name to be a string. This is also important because you can have additional properties beyond what is specifically specified in a type. So let's say John also has a height of, I don't know, a certain number of centimeters. John is still a person because he has all of the required properties of a person and he has all these extra properties. Most of the time with TypeScript, you're only declaring what are the minimum number of properties or minimum properties I need to have, and you're not really worried about if there's extra information that you don't necessarily need. Another fantastic thing that you can do with TypeScript Inference is the concept of type narrowing. Oftentimes you will have type unions. For example, in this case we have dirty data, which is an array of either string values or null values. Now this is kind of difficult to work with because we there's lots of things we can do with a string and not as many things that we do with null. And we want to make sure that anytime we access something from this array, we know what type it is. What we can do is we can narrow down this type. We can do something to say, hey, we're going to get rid of all of the null values in the array, and then TypeScript is automatically going to infer that once we get rid of all of the null values, we are only going to have string values. So let's try this. Let's say const clean data equals dirty data dot filter, and we are only going to return the values that are true. So this just evaluates to true if it's a string because the strings are truthy, and it will evaluate to false because if there's a null value, because null values are falsy, and then don't worry about empty strings. If we want it to be really robust, we could say return true if the type of the value is a string, right? So now we started off with some dirty data and we are getting rid of certain values. In this case, all of the values that are not type of string. And then TypeScript is going to automatically know that anything we get from the clean data is going to be a string. So we could say const my dirty would be some value from dirty data, at 0. And even though here we can see it's a string, it doesn't know. It knows that anything in this array could be string or could be null, so this is not as useful. We don't know for sure whether or not this is a clean or a dirty value. But if we get something from clean data 0, not clean, this is 100% going to be a string. This is also extremely useful within a function that accepts a union type as an argument. Let's say we had a function birthday wish, which is going to take either a person which could be either of type person or type null. And we want to give them a proper birthday wish. What we might be tempted to do is say, hey, return person, do a template string and say happy birthday person dot name. Don't worry about that, right? But this is gonna throw us an error, right? Because we don't know for sure if this is a person or not. It could be null, and if it's null, then this is gonna throw an error. And as you saw, we could do something like this, but it's not ideal because we might want to do something different if the person is null. So what we can do is we can break this function into two parts. We can say if person, this would mean if person is truthy, and if person is null, it's going to be falsy. So here we're going to do something, and otherwise we're going to do something else. Here we could say console.log hello person.name. This is a safe operation and it's not going to throw an error because we've broken our function into two parts. We have only two possibilities of what a person can be. It can either be a person or a null. This section of code, we know 100% for sure that it is a person. This section of code, we know 100% for sure that it's a null. So this same line of code run in a different part of the function with different control flow is going to give us an error. And in this case, it would actually error because this person is guaranteed to be null. So what we could do is instead say console.log I don't even know you. This is an extremely powerful concept that you will see all the time. Very, very often you have data that is very uncertain. It could be multiple different types, multiple different shapes, and you want to do different things and treat it differently depending on the actual shape. TypeScript allows you to run checks on what the properties of the data are, and then correctly infer the type based on the logic of your code, right? So let's give this a shot. We can say birthday wish null, and then birthday wish for John, which was a person. And then we can bun inference.ts. So we have get name, and then we had, oh, here, we actually probably want this to be in an else statement so that it doesn't run both. Oops. Right. So then we have one, I don't even know you, and one, hello, John. Oftentimes, you have to deal with data that is more complex, where a simple check for truthiness is not enough to determine the shape of the data. Like this instance, we have an API response that is some kind of error, and both of these possible options are objects, so both of them would evaluate to true. We have different information in each case, so we need to be able to determine, Is the required permission property going to be defined? Is the retry after property going to be defined? This is called a discriminated union. It is a union of two possible types, our first type, union our second type. And we have a discriminator, which is some key, some value on the type, which uniquely identifies which type it is. In this case, the discriminator is code. Similarly to how we had a literal string type, this is just a literal number type. So what we can do, we can say const handle error, which takes an error of type error response, is we can do one thing. If error.code equals only two possible options, so 429 error, and else if error.code equals, and you'll see there's only one option, right? TypeScript is even smart enough to infer that there. So here we can break it down, and same way we had before, where we determined what type it is based on some control flow. In here, we can say console.log error dot, we know it has the retry after property because it's a 429 error, which means that you're getting rate limited. So we could say console.log retry after error dot retry after, and up here 403 error means that you are forbidden from accessing some command. We can say console.log retry after, or not retry after, sorry, required permissions are error dot required permissions, or required permission singular. But it is smart enough to know that, hey, no matter what, we still have a message property. So even before running this control flow, we could say console.log the error is error dot message, right? Even here, it only lets us access the properties that we know for sure. Up here, we don't know whether it has a retry after property or a required permission property. So it's only going to let us access the message property. Same way, down here, the retry after property doesn't even appear as an option. This is a fantastic pattern you see all the time. It's called a discriminated union, and it really showcases the power of TypeScript. Next, let's move on to another standout feature of TypeScript, and that is generics. And specifically, you say a generic function. So what does that mean? A generic function is a function which can essentially take a type as an argument. You've already been using a lot of these even without realizing it. For example, let's look back at our map function. We could have a string array equals string 1 and string 2, and we could have a num array equals 1, 2. So these are two different arrays of two different types, but we can still use the map function on both of them. We can say numr.map, and in here the value is a number, but when you say string r.map, val, sorry, just hover over. Value is going to be a string, right? If you look at the definition of the map function, you see it is taking in a type. So hang on, if we actually fill this in, string, and we'll just say return the string, right? Hover over map. It's the map function which takes in a string, and if we change it to number, it takes in a number. Generics are not unique to TypeScript. They exist in all languages. However, they really allow you to take TypeScript to the next level. Let's revisit a function we wrote previously. In this case, the map odds function. There's nothing about the map odds function as it's implemented which would behave differently if we passed a different array instead of a string array. We could still apply some function to the odd indexes in our array. So let's convert this into a generic function. To do this, instead of saying string, we need to write t or some other type. The only restriction for writing a generic type is it can't be one of the primitive types that already exists within TypeScript. But let's say, hey, it's not a string type, it's our arbitrary t type. So we can change this, say t and t. Now you're gonna say an error, cannot find t. It doesn't know what t is because it's a type we just made up. To say that this is a generic function, we do greater than sign less than t. And now we have marked this as a generic function that takes in a type and then uses that type for its inputs. So let's look at this. We can call map odds on our string array, and for our function we could just return it. We're not mapping anything, and we could also map it for our num array, right? So here, based on the fact that this first property is a string array, it's going to infer that this value is going to be a string and enforce that this return type is also going to be a string. For instance, we could say val.length, and this is going to error because this is a string, which is the type we're passing in, which means this has to be a string and this has to be a string, but it says type of number is not assignable to type string. Again, we don't have to even pass in. We don't have to say, oh, this is map odds string, like so. It's inferred for us. Even though this is perfectly good syntax, it's completely unnecessary. So this is a generic function. Even though in the example we just went over, it didn't necessarily make sense to explicitly say the type of our generic function, there are certain situations where it does make sense. Let's say we wanted to have a set of usernames to make sure that no two people could have the same username. A set is just a grouping of objects that doesn't have any duplicates. In this current situation, we could add usernames of any type, right? Because it is set unknown. Then we could do usernames dot add user1 and also usernames dot add null, right? this is normally not the behavior we want. So most of the time with a generic function, if you want to explicitly state the type, you can do so with r greater than and less than signs and say what type it's going to be, which will generate a type error if we violate that type. Let's look at some more generic types that TypeScript provides natively. The first is a record type. When you see a record type, I want you to think that it is essentially an object. However, the actual object type can be anything, because at the end of the day, everything is an object in JavaScript, right? If we wanted a function, say const decode, and say code is of type object, and then do something, we could call decode hello, because hello is technically an object. There's like methods we can call on hello. We could call hello.charat or hello.length. So what we really want to do is do a record type, which represents the thing we typically think of where you have keys mapping to values. In this case, we want to define both the type for the keys and the type for the values. So here we just have strings mapping to strings. So say string, string. And then if we had something else, if we had an object which mapped strings to numbers, cipher with an H, this type will properly describe what we want to do. So we can say decode my cipher. That does not throw a type error, but decode cipher will throw a type error because it needs to map a string to a string, and in this case we have a string mapping to a number. How would we go about doing something like this? We have a cipher which maps letters to other letters in the alphabet, something like for creating a secret code. Let's say we had some array of characters. So we could say const code equals A, D, C. And we want to decode this, map A to C, D to F, C to E, so that we get the actual decoded values. With what we've learned so far, you might think that we could say, hey, we are going to take in our code array, which is just going to be an array of strings. So code, which would be a string array. And then what we want to do is we want to return code.map, and then we want to map the value to the mycipher value. But we have a major issue here. This is just any old string, and this could be undefined, right? It's saying that it implicitly has any because it doesn't know whether or not this is going to be defined or not. And if we look at the result, we don't get our nice type inference. It just says any because we don't know if this is type safe, right? If we passed in a bad code, which has characters that don't exist in our cipher, we could have ASDF 123, then our function is not going to be able to tell whether or not we're able to decode this array, right? Decode code is fine, and decode bad code is also fine. How can we make this throw a type error? What we have to do is we have to use the key of operator. Similar to how before we had the type of operator, which returns the type of some value, the key of operator will say if something is a key within an object. So to do this, we can say that code has to be a key of the type of my cipher. And it has to be an array of those values. So let's break this down. My cipher has a specific type. If we hover over it, we can see it. The type is the object with A, B, C, D, E, which all map to strings. And then we know for sure that this access is going to be valid because we know that the value is going to be a key within my cipher. And we get our type inference that this is actually going to be a string array. Now, we still have one little type error here. The issue is that code and bad code are both being inferred as string arrays, but we need to explicitly state that code can't take any string. It has to take keys of my cipher. So all we need to do is enforce that type there, and we will avoid our type error. And this is also useful because if we try and say code.push, something that's not a key, right, then we'll get our type error. Now let's think about how we could make our existing decode function more useful using generics. Currently, we are stuck only using this statically defined my cipher. However, we could rewrite this to instead take the cipher as an argument, and then we could use it with any cipher. So let's give this a shot. Let's say const decode dynamic is a function, and we're going to first have to take in a code and then also have to take in a cipher. We want this to be a generic function, so we're going to state that there. We want the cipher to be of type, our generic type, and our code has to be an array of keys, key of t array, like so. So now we can just copy, say, return code.map, map our value to the value we pass in. So cipher value, like so. And then we could pass in my cipher instead of having it be constrained. So we could console.log decode dynamic, which takes in code and my cipher. Let's test this out. Say fun generics.ts, and we get our code is mapped like so. And if we wanted to write a different cipher, say const my cipher 2, which could just have different mappings. We'll keep the keys the same for simplicity's sake, but we have different mappings. And we can still run it. And, oh, I need to actually type in my cipher 2 and get our result with our different mappings. However, we are going to run into a little bit of a problem with this implementation. That problem being that this T generic type is completely open. We can pass in any type and we will not get a type error because this doesn't, it's just a generic type. It can be anything at all. So we could run into a really interesting situation. Let's say we had a string and we passed in as our array length. Now, why is this okay? Why are we allowed to do this with our current setup of this function? If we look at the type sense options of what are all of the things it's recommending we could type in, you'll notice that all of these are properties on a string. For example, you can slice a string, you can get the length, you can say, hey, does a string include something? So these are all technically keys of strings, right? Because we can say, const my string equals hello, and then say my string dot all of these different things. So really what we need to do is we need a way to say, hey, this is a generic type. We don't want to explicitly specify right off the bat what type it's going to be, but we need to be able to narrow it down a little. So it can't be any type. It can only be a generic thing that is a certain subset of types. The way we do this is with the extends keyword, which is going to say what subset of types can our generic type be. So in this case, we say our generic type T extends the record type. And in this case, we just want our record to be strings mapping to other strings, right? And close that. Once we do this, we get the proper type error because this string is not a record type. So only allowed to do something like mycipher2 and the actual keys of mycipher2, like so. One final useful thing we're going to cover is a built-in utility type to TypeScript. A utility type is just some type that helps you construct a type from some other type. There are quite a few within TypeScript. Many of them are very situational, but the omit type, which lets you have an initial type and omit certain properties from it, is rather useful. Let's say that we wanted to write a function to generate a student ID, and from that then return a student. We could say const generate student ID will take a student and generate the ID. And so we need a student, and for now we'll say student. But here's the issue. This student has to already have a student ID. So if we were trying to create a new student and give them name, Catherine, and grade 12, we can't pass this into generate student ID because generate student ID, new student, because it expects the ID to already exist. So what we need to do is we need to say omit student and then pass in the property that we're trying to omit. So in this case, it is student ID, like so, and there our type error disappears. If you want to omit multiple properties, then you just do an OR operator and include the other properties you're trying to omit. And now both the name and the student ID are omitted, so this wouldn't throw an error if we only have the grade. Yep. But there is one unique quirk of omit. We could change this type, right? Instead of student ID, maybe we'll just rename it to be just ID, right? And this omit statement is not going to throw an error because it doesn't directly check to make sure that the string you pass in is actually a key of this type. So that leads us to first challenge for this video, which is to construct a type based on omit, and we're going to call it StrictOmit, which will throw a type error if you omit a property that does not exist on the record type. So what we want to do is say something like type StrictOmit, does something with generics here, and you say equals omit and does something with generics here. So give you a second to try it out if you want to pause the video, and then I will show you the solution. So let's do it. Type StrictOmit, StrictOmit. What we're trying to do is we need to say we'll take in any type t here, but this has to be a key of t. Otherwise, we want to throw a type error. So we'll say k extends key of t. And then we pass those into the omit function, or not function, sorry, the omit type, tk, like so. And let's try this out. If we say, if we redeclare this function, generate student ID strict, and we, instead of using omit, use our StrictOmit, we get this error right here because student ID does not exist as a key, and instead we are omitting ID, and it still works the way we expect. Generate student ID strict, like so, works for new student, and we can still do our OR operation, grade, and then we could delete grade from new student and not get the type error. But if we deleted that, we do get the type error. So there you go. That is all we're going to cover today for generics. There are some more very niche things to know, but this is more than enough for you to get started. Final concept for today with TypeScript is the idea of casting. Unfortunately, although most of the time you can infer the types of data based on usage, sometimes you run into situations where TypeScript just doesn't know exactly what to expect. For instance, let's take this function we used last time to get the base experience of a Pokemon. TypeScript infers it as a promise that returns any type. This is because it doesn't know what this API response is going to be, and it doesn't know what the type of data.baseExperience is going to be. However, we know that this is going to be a number. So if we want to use this later and ensure that the user of this function knows that it's going to return a number, we can do what is called cast the any type down to a more specific type. So we can say as number, and then this will say that it is a promise that returns a number. This process of casting is essentially overriding the TypeScript compiler and saying, hey, in this specific situation, don't worry about your type inference. I know based on how I have written this code, how this code is going to behave, and I can tell you what type it is going to be. Additionally, it's important to know that TypeScript has a type called any. So we could say const my value as any, and this we could set to a string, and then later, actually we need to make it a let so we can reassign it. We could set my value to a number, and later we could set it to an object, which has some key and some value. Basically, when you use the any type, TypeScript is not going to do any type inference. It's not going to throw any type errors because you're saying that this could be anything. However, this has some major just things to be aware of. Anytime that you are using something that has type any, you can run into errors without having any warning. No pun intended. So for example, if we were to console.log my value dot key dot property dot subproperty, subproperty, right? And then we could go bun casting.ts. We're gonna get undefined because TypeScript just doesn't know what this is. Again, you need to sort of be able to understand how the any type works, but you should almost always not explicitly set something to any, and you can also set your TypeScript compiler to throw an error and prevent you from setting something explicitly to any. However, if you are using some external library or some function that returns an any value, you can cast it down to be a specific type so that it is more useful elsewhere. So just be warned, everything we learned in this video can get thrown out the window if you use the any type, and it can make your code much riskier and more likely to error. And there you go. That is your comprehensive introduction to all the TypeScript that you're going to need for the rest of this course. As a reminder, if you want to look at the completed code at any time, we have it all right here. We covered basic TypeScript, typing functions, type inference, generics, and also casting. If you want to practice some of the things we talked about in this video, this lecture has a corresponding assignment with some practice problems. There is a starter code repository for it. You can just use this template to create a new repository, go through this, and practice all of the problems we have for you. Great. Next time we are going to dive into front end and start covering React. I hope you enjoyed, and take care.